Hello and welcome again to YCP Chemistry Labs, York College of Pennsylvania's YouTube channel dedicated to get you ready for lab each and every week. Today in the General Chemistry 2 curriculum, we're talking about the enthalpy of vaporization of liquids exercise. It's not really an experiment that we're doing this week. Rather, we're doing a computational analysis to help us determine the enthalpy of vaporization and boiling points of liquids. So let's review some of the concepts that are at work as part of this exercise, and I'll run you through the bare bones of the types of calculations that we're going to help you do this week. We'll be doing a lot of work in Excel spreadsheets in lab, very much like what we did for density calculations back in our Chemistry 1 curriculum if you took General Chemistry 1 here at York. All right, and I'll wrap up by briefly addressing a few of the points in the PreLab questions as well. So vaporization, all liquids, believe it or not, vaporize pretty much regardless of what the temperature is. That's why we have humidity in the air outside, but any liquid sample that we have is capable of converting some part of it itself into the gas phase. And when gas is produced by that liquid, gases, as we now know by what we've studied in class, cause pressure. That's why we have the term vapor pressure. It's referring to the pressure of the gas generated by the vaporized liquid. So that's what vapor pressure means. Now this vapor pressure depends strongly on the temperature, all right? And you should all be somewhat familiar with the idea that in the summertime it's a lot more humid than it is in the winter time. That's because the temperature is higher and the air is capable of holding a lot more water vapor, and water vaporizes more at that higher temperature on a typical summer day than it does on a cold winter day. All right? Unfortunately, it's not a straight or linear relationship. And that's where this work gets just a little bit tricky, because it's not just a straight line. Okay? Now the ability of a liquid to vaporize also depends on the type of intermolecular force, IMF, present in the sample. This is something that we cover in our textbook in the General Chemistry 2 class, and maybe you're just getting started with this topic now. But the intermolecular forces are what holds molecules to one another, not the chemical bonds that hold the atoms together to form a molecule, but rather what makes one molecule want, if at all, to stick or cling to another molecule of the same material. And the stronger that intermolecular force, the harder it's going to be to vaporize that liquid and to have it escape into the gas phase, because they want to hold together. All right? So that strength is often characterized by what we call the enthalpy of vaporization. Delta H, and enthalpy, the classic enthalpy symbol, and then the subscript VAP for vaporization. So how much energy, in other words, does it take to vaporize 1 mole of the liquid? That's what the enthalpy of vaporization would be. The higher that number is, in general, we can conclude that the stronger the intermolecular force. Now the equation that ties all of these variables together is what's known as the Clausius-Clapeyron equation. All right? It has a couple of different formats depending on the context in which you might want to use it. And as part of our work in lab, we're going to use it in the 2 most common formats. For any single data point, what's the pressure at a particular temperature? Here's the relationship. The logarithm, the natural logarithm of that vapor pressure is equal to negative, this is the enthalpy of vaporization, divided by R, which is the ideal gas constant. Although in this case R is not in its typical set of units of atmosphere liters per mole Kelvin, as we learned for our gas laws chapters. It's in a different set of units, 8.314 joules per mole Kelvin. All right? The joule is the SI unit of energy. You've heard of it in kilojoules, of course. And since we are relating all of these terms to an energy, we need R to be in a set of units that involves energy. So it's the same concept, R, as when we used it in the ideal gas law, but now it's just expressed in a different language, a different set of units, 8.314 joules per mole Kelvin. So delta H divided by R and T, and then there would be a constant. That constant's going to be unique to each different substance, so I just generically put it up there as a constant for right now. Now, any two data points for pressure and temperature can be related to one another. And if we started to think graphically, 2 points define a line on any XY graph that you might make, right? And so if we looked at 2 points, there's an interesting relationship, and this is often called the 2-point Clausius-Clapeyron equation. The logarithm of the second pressure divided by the first pressure is equal to negative delta H over R, very similar to what we have here. But also, now we have, in parentheses, 1 over temperature 2 minus 1 over temperature 1. And the constants are gone because if we subtract 1 point from the other, those two constants would be equal and they would cancel out. They would subtract out. That's why there's no constant over here in this form right here. This is a useful form that once we know one vapor pressure at a particular temperature, if we know the enthalpy of vaporization, we can solve for another vapor pressure, or perhaps what temperature we need to create a particular vapor pressure. Or if we measure two vapor pressure points, we could calculate the enthalpy of vaporization. All right? So that's often how this is used. This equation, on the other hand, even though I said it's for a single point, looks suspiciously like a y equals mx plus b format, which matches a straight line, right? This is the format of every straight line. Now, I said that vapor pressure and temperature wasn't linear, but what is linear is the logarithm of vapor pressure related to 1 over temperature. And a graph of logarithm of pressure versus 1 over temperature should produce a relatively straight line. The slope of this line, the m part, since x is 1 over t, here's my 1 over t, the slope is the rest of this product that we're looking at right there, or negative delta H VAP over R. So if we have a lot of vapor pressure data, we can make a graph of the logarithm of pressure versus the 1 over temperature values, put a straight line through it, and get the number for the slope. That number equals this combination, and your enthalpy of vaporization then is simply negative R times m, right? You just multiply the negative and the R over to the other side. So in today's lab, you will be given a set of data, vapor pressure data, and you will make this graph using Excel, and then you will calculate the enthalpy of vaporization. And then we're sort of going to do an inside out here. Once you have the enthalpy of vaporization, then you will come over to the 2-point Clausius-Clapeyron equation, and we'll manipulate this in order to determine the temperature at which we would achieve a particular vapor pressure. All right? Now that particular vapor pressure that we're hoping to achieve is 1 atmosphere. 1 atmosphere is special because that's what we think of as the normal atmospheric pressure. So that's how much pressure the atmosphere normally applies on us and everything around us. When a liquid pushes out with 1 atmosphere of pressure, it's going to boil. That's the proper definition of boiling. Liquid producing the same vapor pressure as the atmosphere's pressure. As the prevailing atmospheric pressure. So if we go up a mountain, the atmospheric pressure is lower, and therefore liquids boil at lower temperatures at higher altitudes because there's less atmosphere pushing down on them. Therefore the liquid doesn't have to push out as much until it matches and equals the atmosphere's pressure. And so water will boil at about 95 degrees Celsius in some higher altitudes in the Rockies in the United States. And it'll boil as low as the mid-70s on some of the highest mountains on Earth, actually. Mount Everest, for example. All right? It looks just the same. It's just not as hot. But coming back to the Clausius-Clapeyron equation then, we can predict what temperature this would be using the two-point version of the Clausius-Clapeyron equation. So ln of P2 over P1 equaling negative delta H VAP over R 1 over T2 minus 1 over T1. In our work in the lab today, we're going to find delta H VAP from the graph. Then we're going to use the delta H VAP and a pressure temperature. So as I was saying, once we find the enthalpy of vaporization from our graph, we'll use one of our known pressure temperature points to find the new temperature, T2, to create a desired vapor pressure of 1 atmosphere. That would be the boiling point, in other words. T2, when we define P2 as 1 atmosphere, T2 is the boiling point, or what we call the normal boiling point, because that's normal atmospheric pressure. So there's just the algebraic manipulation of this equation to figure out how to do that. So we're after T2 here. So let's carefully walk through some of the algebra here. First, we want to get rid of this stuff, right? Bring it over here. So R is in the denominator, so it would get multiplied over to the left side. Delta H is in the numerator, so it would become divided by. We have a negative sign, so we'd multiply both sides by a negative. So we basically just flipped that and bringing it over. ln of P2 over P1 stays untouched. That leaves us with 1 over T2 minus 1 over T1. Now we can just add the 1 over T1 to this side. So 1 over T1 would be added. So we might as well have it be first minus the R over delta H VAP ln P2 over P1. And then T2 being in the denominator, unfortunately the whole thing needs to be flipped. This is a pretty challenging fraction. We can't just flip P1 and P2 into the numerator, flip R and H into the numerator, because it's because it's in the argument of a natural log, and because there's a sum here, or a difference. So the easiest way to do this is just after you numerically had this, to take the reciprocal. That is the, quote, flipping that you might do, right? Taking the reciprocal. So I'm just going to write all of that raised to the negative 1 power, because that's what you do to this. You've essentially flipped it, raised it to the negative 1 power, and so you have 1 over this entire expression. And in the computer, that'll be quite easy to do. So when you are setting up in the lab, and by the way, this will be very important for your pre-lab questions. Essentially, this is how you would do PreLab question 3, you're now into a position where you can substitute your data given to you. PreLab question 2 would be a little similar to this, except that you would have solved for the delta H in PreLab question 2. So you still would have taken the R over and the negative sign, and then you would just divide by this entire 1 over T2 minus 1 over T1. So you'll have negative R ln P2 over P1 divided by the 1 over T2 minus 1 over T1 expression for number 2, PreLab question. All right. Now, in the context of what you're doing in lab today, feel free to ask questions and work with other students, but what you'll start with are pressures and temperature values in an Excel spreadsheet. So you might have a number of pressure values and a number of temperature values, and we're trying to make a graph, remember, that has ln of P on the y-axis and 1 over T on the x-axis. So you'll need to generate a column to take the ln of P, and in a spreadsheet you can simply do that by typing equals ln of and then referencing whatever cell this is. So if perhaps if this was A2, you would say equals ln of A2, and it will take that, and then you just fill that formula down. Using you can grab the little square, and then that's the bottom corner of the cell, and pull it down. And then the temperatures, first of all, the temperatures need to be in Kelvin. So if they're given to you in Celsius, you have to convert them to Kelvin. But then you'll need 1 over the temperatures. So again, rather than calculating each of these by hand, a spreadsheet can very quickly just say equals 1 divided by, if this was row B, or let's call it row B, that would be 1 divided by B2. And again, then you can fill that value down. Then you'll have the data for your graph. The trickiest formula that you'll have to write into Excel will be this one. You'll need to turn this into an Excel formula, but remember, each of these, like T1, it won't be T1, it will now be a cell that you'll reference, like cell B2. And then the P1 would be cell A2. So you'll type in place of these variables specific cells, or in the case of delta H, you'll have calculated delta H from your graph. So you'll have a number there, and you'll have a number for R there. Okay? And then you'll be calculating the boiling point of your liquid. So everyone will work with water sort of as a practice, and then you'll be given a second liquid, data for a second liquid to figure that out. The same treatment, I'm sorry. You'll apply the same Clausius Clapeyron analysis to a different liquid. Okay? All right, so you're pretty well set. One last thing, I've already talked a little bit about two of the PreLab questions. The first PreLab question asks about the amount of energy required when vaporizing a liquid. So liquids, when they vaporize, occur at constant temperature. Now energy, heat specifically, is quantified in only 2 ways we've learned already this semester. These are the only 2 formulas that we've used to calculate the amount of heat required to do something or that's released. I just said a second ago that vaporization occurs at a constant temperature. Because of that, we know we're not using this formula. We also know there's something called an enthalpy of vaporization, a delta H. So that really should have targeted us to using this formula right here to answer the first PreLab question. So we're given, I believe, the enthalpy of vaporization, of the liquid. And it's simply a matter of maybe converting the mass of the liquid into moles, and then that will give us the heat required to vaporize the given quantity of the liquid. So you should be all set now. reviewed the 3 pre-lab questions, at least the formulas that are at work, and set the stage for what you're studying in this exercise. All right? I'll wish you good luck, and I'll see you next week when we talk about, I believe, melting points of organic compounds.